Hello, wanderer of the night. Welcome back to the Midnight Explorer. Before you close your eyes tonight, before you drift into dreams, let me tell you a story. Not a story of kings or kingdoms, not of wars or empires, but something far older, far vaster. Tonight, we're going to talk about everything. And I mean everything. We're going to explore the cosmos, the universe itself, the greatest mystery that has ever whispered to the human heart. We'll trace the footsteps of ancient shepherds who looked up at the night sky and wondered. We'll sit beside philosophers in candlelit rooms. We'll stand with scientists at the edge of understanding, peering into the infinite dark. This is a story about how we came to know our place in the universe, about how tiny beings on a tiny world learned to measure infinity, about how we discovered that we are made of stardust, born from the same ancient fire that lit the first stars. So pull your blanket close, dim the lights, and let me take you on a journey through time and space, through the long, beautiful history of cosmology, the science of everything. Are you ready? Let's begin. Close your eyes for a moment and imagine this. It is 40,000 years ago, maybe more. You are sitting outside a cave in what will one day be called France, or perhaps Africa or the Middle East. The exact place doesn't matter. What matters is this. Above you, the sky is doing something impossible. The sun has set, taking its warmth and light with it. The world has grown cold and dark. But the darkness is not empty. No, the darkness is alive with light. Thousands upon thousands of pinpricks of light scatter across the black canvas above you. Some are bright, some barely visible. They form patterns, shapes that your mind automatically tries to recognize. A hunter, a bear, a river of light flowing across the sky like milk spilled by the gods. You don't have words for astronomy or cosmology. You don't have telescopes or mathematics or physics, but you have something just as powerful. You have wonder. What are those lights? Are they holes in the fabric of night through which the light of heaven shines? Are they the ancestors who have passed beyond this world? Are they the eyes of gods watching over you? This moment, this simple act of looking up and asking, "What?" This is where cosmology begins. Not in a laboratory, not in a university, but in the human heart, in that deep, ancient hunger to understand what we see, to find meaning in the vastness above us. The first cosmologists were storytellers. They were the elders who sat by fires and explained the sky to children. They watched the patterns, noticed that certain stars appeared at certain times. They saw that the moon changed shape in a rhythm, waxing and waning like a beating heart. They noticed that the sun traced a path across the sky, higher in summer, lower in winter. And they wove these observations into stories, stories that helped their people understand when to plant crops, when to migrate, when to prepare for winter. The sky became a clock, a calendar, a map, and a book of sacred stories all at once. In Mesopotamia, the ancient Sumerians, 5,000 years ago, would climb to the top of ziggurats, those magnificent stepped pyramids, and they would chart the movements of the stars with remarkable precision. They saw that 5 special stars moved differently from the others, wandering across the background of fixed stars. They called them wanderers. We call them planets. In Egypt, priests would watch for the rising of the star Sirius just before dawn, knowing that when it appeared, the Nile would soon flood, bringing life to the desert. The sky and the earth were connected, they believed. As above, so below. In China, astronomers kept meticulous records of celestial events, comets, meteors, eclipses. They believed the heavens reflected the state of the empire, that chaos in the sky meant chaos on earth. To understand the stars was to understand the fate of kingdoms. And in the Americas, the Maya built observatories and developed calendars of stunning accuracy, tracking Venus with such precision that their calculations differ from modern measurements by only a few hours over thousands of years. But notice something beautiful here. Despite their different stories, despite their different gods and different languages, all of these ancient peoples were doing the same thing. They were watching. They were recording. They were trying to find patterns in the chaos, order in the seeming randomness of the night sky. They were the first cosmologists, and they gave us something precious. They taught us that the universe follows rules, that it has patterns, that it can be understood, at least a little, by creatures as small and brief as us. Now let us step forward in time, to a place where the Mediterranean Sea sparkles in the sunlight, where olive groves sway in warm breezes, where marble temples gleam white against blue skies. We're in ancient Greece, around 2,500 years ago, and here something remarkable is about to happen. Here, human beings are about to take the first steps towards a scientific understanding of the cosmos. Imagine walking through the streets of Miletus, a prosperous Greek city on the coast of what is now Turkey. You enter a school, one of the first schools of philosophy in the Western world, and here you meet a man named Thales. Thales is looking up at the night sky, but he's not just telling stories. He's asking a different kind of question. Not which god put the stars in the sky, but what are the stars made of? How do they move? What laws govern them? This is revolutionary. This is the moment when mythology begins to give way to philosophy, when human beings begin to believe that the universe operates according to natural principles that we can discover through reason and observation. Thales believes that everything is made of water. He's wrong about that, but it doesn't matter. What matters is that he's trying to find a natural explanation for the cosmos, not a supernatural one. He's asking the right questions, even if he doesn't have the right answers yet. His student, Alexander, goes further. He proposes that the Earth floats freely in space, held by nothing, surrounded by celestial spheres. He's wrong about the details, but astonishingly he's grasped something profound. The Earth is not the foundation of everything, sitting at the bottom of creation. It's suspended, floating in something much larger. Then comes Pythagoras, the mathematician, who looks at the sky and sees not just beauty, but geometry. He hears music in the movements of celestial bodies, the music of the spheres, he calls it. He believes the universe is mathematical at its core, that numbers are the language of reality. And he's right. 2,000 years later, we'll discover that mathematics is indeed the language we need to understand the cosmos. But Pythagoras is feeling this truth more than proving it, sensing it in the harmony of numbers and the patterns of stars. But the Greek philosopher who will change everything, who will dominate cosmological thought for nearly 2 millennia, is yet to come. His name is Aristotle. Picture him, a middle-aged man with a keen, penetrating gaze, pacing through the Lyceum in Athens, surrounded by students. He's thinking about the cosmos, building a complete system to explain everything he sees. And the system he builds is beautiful, elegant, logical, and almost completely wrong. But let's not judge him too harshly. Let's understand what he was trying to do. Aristotle observes that everything on Earth, rocks, rain, leaves, animals, everything falls down towards the ground. He reasons that Earth must be at the center of the universe, and that all heavy earthly things are trying to return to this natural center. He looks up and sees the moon, the sun, the planets, the stars. They don't fall down. They move in circles, eternal, perfect circles. Therefore, he reasons, they must be made of something different from earthly matter. He calls this substance ether, a perfect, unchanging celestial element. In Aristotle's cosmos, the Earth sits still at the center. Around it, transparent crystalline spheres carry the moon, the sun, the planets, and the stars, all rotating in perfect circles. Beyond the furthest sphere lies the realm of the prime mover, the first cause, the unmoved mover that sets everything else in motion. It's a cosmos that makes sense. It matches what our senses seem to tell us, that we're standing still and everything else is moving around us. It's a cosmos with order, with purpose, with a place for everything and everything in its place. and it's a cosmos that will trap human understanding for almost 2 millennia. But before Aristotle's geocentric cosmos becomes dogma, there's one Greek who dares to imagine something different. His name is Aristarchus of Samos, and around 270 BCE, he proposes something shocking, something that won't be seriously considered again for almost 2 millennia. What if, he suggests, what if the sun is at the center and the earth moves around it? Think about how radical this is. It contradicts everything our senses tell us. We don't feel like we're moving. The ground beneath our feet feels solid, still, unmoving. The idea that we're actually hurtling through space at tremendous speed, spinning like a top while simultaneously orbiting the sun, it seems absurd. Aristarchus's contemporaries think he's crazy. They ignore him. Now we must walk through darker times, though perhaps darker is not quite fair. The centuries that follow are not dark for everyone and not dark in every way. The Roman Empire rises and falls, libraries burn, knowledge is scattered, preserved in fragments, carried by monks and scholars across continents. In Europe, the chaos of the Dark Ages settles like a long winter. But winter is not the end of the story. It's just a time of waiting, of seeds lying dormant in frozen ground. And while Europe sleeps, other parts of the world are dreaming brilliant dreams. In Baghdad, in Cairo, in Cordoba, Islamic scholars are preserving and expanding upon the Greek knowledge that Europe has largely forgotten. They're translating Aristotle and Ptolemy into Arabic. They're building observatories. They're measuring the movements of planets with unprecedented precision. A scholar named al-Battani refines astronomical tables with such accuracy that European astronomers will still be using his work 1,000 years later. Another scholar, al-Sufi, creates a book of fixed stars, complete with beautiful illustrations, cataloging everything visible in the night sky. Ibn al-Haytham, known in the West as Alhazen, is conducting experiments with light, laying the groundwork for the science of optics. He's asking how we see, how light travels, how our eyes and the objects we observe interact. He's doing science, real, experimental science, at a time when most of Europe is concerned with theological debates. Meanwhile, in India, mathematicians and astronomers are developing sophisticated models of planetary motion. They understand trigonometry. They use the concept of zero, a revolutionary idea that will eventually transform mathematics. In China, astronomers are still keeping their meticulous records, still tracking comets and eclipses, still watching the heavens with patient, careful eyes. The point is this: cosmology never died. Human curiosity never died. It just moved, flowed like water, finding new channels, preserved itself in different languages, different cultures, different hands. And slowly, gradually, like a sunrise that begins with just a hint of light on the horizon, Europe begins to wake up. It's the 12th and 13th centuries now. Scholars are rediscovering the works of Aristotle, translated from Arabic back into Latin. Universities are being founded: Oxford, Cambridge, Paris, Bologna. Places where people can gather to argue about ideas, to question, to study. A Dominican friar named Thomas Aquinas is working to reconcile Aristotelian philosophy with Christian theology. He's building an intellectual cathedral, a system of thought that encompasses both heaven and earth, both faith and reason. And Aristotle's geocentric cosmos? It fits perfectly with religious doctrine. The earth at the center, humanity at the center. Everything else revolving around us, it aligns with the idea that we are God's special creation, that we are the purpose of everything. The Catholic Church embraces this cosmology. It becomes not just science, but sacred truth. To question it begins to feel like questioning God himself. But here's something beautiful about human nature. We can't stop asking questions, even when it's dangerous, even when it's forbidden, even when the answers might shatter everything we believe. And in the 15th and 16th centuries, the Renaissance is flourishing across Europe like a garden after rain. Artists are studying perspective and anatomy. Explorers are sailing to new worlds. Inventors are tinkering with new machines. The printing press is spreading ideas faster than ever before. And in this atmosphere of curiosity and creativity, a quiet Polish scholar is about to change everything. His name is Nicolaus Copernicus. Picture him, a canon of the Catholic Church, living in a tower in Fromberg, a small town in what is now Poland. He's in his 60s now, an old man by the standards of his time. He's been working on a manuscript for years, decades really, and he's been reluctant to publish it because he knows what it will do. It will overturn the cosmos. Copernicus has been studying the old Greek texts. He's found references to Aristarchus's heliocentric hypothesis, the sun-centered cosmos that everyone dismissed as absurd. And Copernicus has been doing calculations, working out the mathematics, and he's discovered something stunning. If you put the sun at the center instead of the Earth, everything becomes simpler. The complicated loops that planets seem to trace across the sky, what astronomers call retrograde motion, suddenly make perfect sense. They're just an illusion caused by the fact that we're watching from a moving platform. It's like being on a train and watching another train on a parallel track. Sometimes it seems to be moving forward, sometimes backward, but really it's just a matter of perspective, of relative motion. Copernicus's system isn't perfect. He still thinks planets move in perfect circles, which they don't. He still includes some of the complicated epicycles of the old system. But the core insight is revolutionary. We are not the center. The Earth is a planet just like the others. We are moving through space, spinning and orbiting, part of a cosmic dance rather than the still point around which everything revolves. In 1543, on his deathbed, Copernicus finally publishes his work, De Revolutiones Orbium Celestium, on the revolutions of the celestial spheres. Legend says that a printed copy was placed in his hands as he lay dying, and he woke up just enough to see his life's work in print, then passed away peacefully. Whether or not that story is true, this is true. Copernicus has lit a fuse. The explosion will take time, decades even, but it's inevitable now. The center is not holding. The cosmos is about to transform. It's a cool evening in Padua, Italy, in the year 1609. A middle-aged professor of mathematics has climbed to the roof of his house, carrying an unusual device. A tube about 3 feet long with carefully ground glass lenses at each end. His name is Galileo Galilei, and he's about to see what no human being has ever seen before. Galileo didn't invent the telescope. That credit belongs to Dutch spectacle makers who discovered almost by accident that if you arrange 2 lenses in a tube in just the right way, distant objects appear closer. The invention spread across Europe like wildfire. A new toy, a curiosity, useful perhaps for sailors or soldiers. But Galileo understood something that others didn't. This wasn't just a toy. This was a key that could unlock the heavens. He had heard rumors of the Dutch invention, and with his knowledge of optics and his skill with instruments, he built his own telescope. Then he built a better one, then an even better one. Each iteration brought the cosmos a little closer, a little clearer. And then, on a January night in 1610, he pointed his telescope at Jupiter. Try to imagine what he felt in that moment. He expected to see a bright dot, like Jupiter appears to the naked eye. Instead, he saw a tiny disk, a clear sign that Jupiter had size, dimension, substance. And even more astonishing, he saw 3 small stars near it, lined up in a row. Interesting, he thought, but not too unusual. Stars are everywhere. The next night, he looked again, and the 3 stars had moved. They were on the other side of Jupiter now. That's odd, he thought. That's very odd indeed. Night after night he watched, and slowly the truth became undeniable. These weren't stars at all. They were moons. Moons orbiting Jupiter, a miniature solar system right there in the night sky. And if Jupiter had moons orbiting it, then not everything in the universe was orbiting the Earth. The old geocentric model demanded that everything orbit our planet, but here was proof, visible, undeniable proof, that at least some things in the cosmos obeyed different rules. Galileo's hands must have shaken as he made his sketches, recording the positions of Jupiter's moons night after night. He was witnessing something no one else in history had seen. He was watching the machinery of the cosmos at work. But he wasn't finished. His telescope had more secrets to reveal. He turned it toward the moon, expecting to see a perfect, smooth sphere, because Aristotle had taught that celestial bodies were perfect, unchanging, made of pure aether. Instead, Galileo saw mountains, valleys, craters. The moon was a world, rough and complex, with terrain as rugged as Earth's own. It wasn't made of perfect celestial substance. It was made of stuff, regular, rocky, earthly stuff. He pointed his telescope at the sun, carefully using a projection method because even Galileo wasn't reckless enough to stare directly at it through a telescope. And he saw sunspots, dark blemishes moving across the sun's surface. The sun, too, was imperfect. It was changing, rotating, dynamic. He looked at Venus and saw that it went through phases just like the moon, crescent, half, full. This only made sense if Venus was orbiting the sun, not the Earth. The geometry was clear, mathematical, undeniable. And when he looked at the Milky Way, that river of light that flows across the night sky, he saw that it wasn't a cloud or a glowing mist. It was stars, thousands upon thousands of stars, too faint to see individually with the naked eye, but there, oh, so very there, crowding the darkness. The universe was suddenly so much bigger than anyone had imagined, so much more full of worlds and wonders. In 1610, Galileo published his observations in a short book called Sidereus Nuncius, The Starry Messenger. It became an instant sensation. Copies spread across Europe. Some people were thrilled, some were skeptical, some were angry. Because Galileo wasn't just reporting observations, he was taking sides in the great cosmic debate. He was openly supporting Copernicus's heliocentric model. He was saying, Aristotle was wrong, the Church's official cosmology is wrong, the Earth moves. For a while, it seemed like he might get away with it. The evidence was compelling. Even some Jesuit astronomers confirmed his observations. The truth seemed inevitable. But Galileo made a mistake. He wasn't content to just present evidence. He wrote a book, a dialogue concerning the two chief world systems, in which he compared the Ptolemaic and Copernican models through a conversation between three characters. One character, Simplicio, defended the old Earth-centered cosmos, and Galileo made Simplicio sound foolish, argumentative, close-minded. The problem? Some of Simplicio's arguments were ones that Pope Urban VIII himself had made. Whether Galileo intended it or not, it looked like he was mocking the Pope. This was not politically wise. In 1633, at the age of 69, Galileo was summoned to Rome to stand trial before the Inquisition, accused of heresy for teaching that the Earth moved. Imagine him standing there, old and sick, he would be nearly blind in a few years, facing the power of the Church, knowing that other men had been burned at the stake for lesser offenses. He recanted. He said he had been wrong, that he would no longer teach that the Earth moved. He said whatever he had to say to save his life. They sentenced him to house arrest anyway. He would spend the last 9 years of his life confined to his villa in Arcerti, forbidden to publish on astronomy. But here's the thing about truth. You can imprison the messenger, but you can't imprison the message. Galileo's observations had been confirmed by too many others. His books, though banned, continued to circulate, and all across Europe, astronomers were building telescopes and looking up and seeing the same wonders he had seen. The genie was out of the bottle. The cosmos had been revealed as something far stranger and more magnificent than the perfect, unchanging heavens of Aristotle's imagination. While Galileo was observing the heavens through his telescope, another man was approaching the cosmos from a different direction, not through observation, but through mathematics. His name was Johannes Kepler, and he was, in many ways, the opposite of Galileo. Where Galileo was bold and combative, Kepler was mystical and deeply religious. Where Galileo focused on what he could see, Kepler was obsessed with finding the hidden harmonies, the mathematical laws that he believed God had written into the fabric of creation. Kepler was born in Germany in 1571 into a time of religious wars and political chaos. He was a sickly child with terrible eyesight, ironic for a man who would help us see the cosmos more clearly than ever before. He became the assistant to Tycho Brahe, a Danish nobleman and the greatest observational astronomer of the age. Tycho had spent decades making incredibly precise measurements of planetary positions, the best observations made before the invention of the telescope. But Tycho couldn't make sense of his own data. He had his own compromise model of the cosmos, neither fully geocentric nor heliocentric, but something in between. When Tycho died in 1601, Kepler inherited his treasure trove of observations, and Kepler had something Tycho lacked, a willingness to let go of old assumptions. For years, Kepler tried to fit Tycho's observations into the Copernican model. Copernicus had said planets orbited the sun in circles, perfect circles. But no matter how Kepler adjusted the circles, no matter how many epicycles he added, he couldn't make the observations match the theory. The problem was Mars. Tycho's observations of Mars were so precise that the errors were tiny, just 8 minutes of arc, less than 1/4 of a degree. Many astronomers would have dismissed such a small discrepancy as measurement error. But Kepler trusted Tycho's observations, and he trusted that God would not create a universe that was almost elegant, almost perfect, but not quite. If the theory didn't match the observations, the theory had to change. So Kepler did something radical. He abandoned circles. What if, he wondered, what if planets don't move in circles? What if they move in ellipses? An ellipse is like a circle that's been gently squashed. It's not as perfect, not as aesthetically pleasing. For 2,000 years, from Aristotle through Copernicus, everyone had assumed that celestial motion had to be circular, because circles were perfect and the heavens were perfect. But what if perfection didn't mean geometric simplicity? What if perfection meant something deeper, mathematical laws that were simple and elegant even if the shapes they produced were complex? When Kepler tried elliptical orbits, everything clicked into place. Mars's orbit fit perfectly. So did the orbits of all the other planets. This was Kepler's first law. Planets move in ellipses with the sun at one focus. But he didn't stop there. He noticed something else. Planets moved faster when they were closer to the sun and slower when they were farther away. He worked out the exact mathematical relationship. A planet sweeps out equal areas in equal times. If you imagine drawing a line from the sun to a planet and then tracing the area that line sweeps through as the planet moves, that area will be the same whether the planet is close to the sun and moving fast or far from the sun and moving slowly. This was his second law, and it was beautiful, a precise, quantitative description of planetary motion. His third law came later, after years more of work. The square of a planet's orbital period is proportional to the cube of its average distance from the sun. This law connected all the planets together in one elegant mathematical relationship. Why does this matter? Why should you care about ellipses and mathematical ratios? Because this is the moment when cosmology transforms from philosophy and observation into genuine science. Kepler's laws are precise, quantitative, and predictive. You can use them to calculate where a planet will be at any future date. You can test them. They work. Kepler himself was ecstatic. He believed he had uncovered the mind of God, that he had found the divine harmonies that structured creation. He wrote, "I thank you, Lord God, our Creator, that you have allowed me to see the beauty of your creation." But Kepler's laws raised a troubling question. Why? Why do planets move in ellipses? Why do they speed up when closer to the sun? What force, what mechanism makes them do this? Kepler himself thought there might be some kind of magnetic force emanating from the sun. He was reaching for the right idea, but he didn't have the mathematics to make it work. The answer would come from England, from a man who was perhaps the greatest scientific mind in human history. His name was Isaac Newton. Newton was born in 1442, the same year Galileo died, a poetic passing of the torch. He grew up in rural England, a curious, obsessive, sometimes difficult personality who showed early brilliance in mathematics. In 1665, when Newton was just 25, the plague swept through England, Cambridge University closed, and Newton returned to his family's manor house in Woolsthorpe. And there, in isolation, over the course of 18 months, this young man had perhaps the most productive period of scientific thinking in history. He invented calculus, he conducted experiments with light, and discovered that white light is composed of a spectrum of colors. And he began working on the problem of motion. What makes things move the way they do? The story goes that he was sitting in the garden when he saw an apple fall from a tree, and he began to wonder, why does the apple fall down? What force pulls it toward the earth? And then, and this is the leap of genius, he wondered, is it the same force that holds the moon in its orbit around the earth? Think about how audacious this is. The apple falls, the moon orbits. They seem completely different. But what if, Newton thought, what if the moon is falling just like the apple? What if it's falling toward Earth but moving sideways fast enough that it keeps missing? It's like throwing a ball. Throw it gently, it falls to the ground nearby. Throw it harder, it falls farther away. Throw it impossibly fast, and it would fall forever, curving around the Earth, never landing, an orbit. Newton worked out the mathematics. He proved that if gravity weakens with the square of distance, meaning if you double your distance from Earth, the gravitational force becomes 4 times weaker, then you get Kepler's laws automatically. The elliptical orbits, the speed changes, everything falls out of the mathematics naturally. But it took him 20 years to publish this work. He was secretive, perfectionist, reluctant to engage with criticism. Finally, in 1687, urged on by his friend Edmund Halley, he published Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. The Principia, as it's called, is one of the most important books ever written. In it, Newton presents his 3 laws of motion and his law of universal gravitation. And he doesn't just assert these laws, he proves them, using rigorous mathematics, showing how they explain everything from falling apples to planetary orbits to the tides of the ocean. Universal gravitation. Universal. That word is key. Newton was saying that the same force that makes an apple fall on Earth makes planets orbit the sun, makes moons orbit planets, makes galaxies rotate. One law applying everywhere in the cosmos forever. The universe, Newton showed, is a clockwork, precise, mathematical, and predictable. If you know the position and velocity of every object, you can calculate its future motion with perfect accuracy. The universe follows rules, elegant, beautiful, universal rules. For the first time, humanity had a complete working model of how the solar system operated. And it worked flawlessly. Astronomers could use Newton's laws to predict planetary positions years in advance, and the planets would be exactly where the calculations said they should be. It was glorious. It was triumphant. It seemed like the universe had finally revealed its deepest secrets. But of course, the universe always has more secrets. Always. The clockwork would turn out to be far stranger than Newton imagined. Let's skip forward now, moving through time more quickly. We're jumping over centuries, watching as Newton's mechanical cosmos becomes the foundation of physics, as astronomy becomes more precise, as telescopes become larger and more powerful. It's the early 20th century now. Queen Victoria is dead. The old certainties of the Victorian age are crumbling. Einstein has just published his theories of relativity, showing that space and time are not fixed and absolute, but flexible, relative, intertwined. And on Mount Wilson in California, an astronomer named Edwin Hubble is making observations that will shatter our understanding of the cosmos once again. But before we meet Hubble, we need to understand what people thought about the universe in his time. In the early 1900s, most astronomers believed that the universe consisted of our Milky Way galaxy and nothing else. Yes, there were fuzzy patches of light scattered across the night sky, objects called nebulae, but most astronomers thought these nebulae were just clouds of gas within our own galaxy, perhaps places where stars were forming. The Milky Way, in this view, was everything. It was a vast collection of stars, perhaps 100 billion of them, floating in otherwise empty, infinite space. Beyond the galaxy? Nothing. Just darkness, extending forever. But there was a debate. Some astronomers wondered whether some of these nebulae might actually be island universes, separate collections of stars, other galaxies far beyond our own. The idea wasn't new. The philosopher Immanuel Kant had suggested it in the 18th century, but without proof, it remained speculation. Edwin Hubble set out to find proof. Hubble had access to the most powerful telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson, and he focused it on one of those mysterious nebulae, the Andromeda Nebula, a fuzzy, oval patch of light visible to the naked eye on clear nights. Night after night, Hubble took photographs of Andromeda, long exposures that captured more light than the eye could see, and he began to pick out individual stars within the nebula. And among those stars, he found several that varied in brightness over time, pulsating stars called Cepheid variables. And here's the crucial thing. Astronomers had already figured out that there's a relationship between how fast a Cepheid variable pulses and how bright it actually is. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it must be. It's like seeing a candle in the distance. If you know it's a standard candle, you can figure out the distance by how dim it looks. Hubble did the calculations, and the answer shocked him. Andromeda wasn't a nebula within our galaxy. It was nearly 1 million light-years away. We now know it's about 2.5 million light-years distant. It was another galaxy entirely, as large as our own Milky Way, filled with hundreds of billions of stars, an entire cosmos of its own. And if Andromeda was a separate galaxy, then probably many of those other nebulae were galaxies too. In one stroke, the universe became unimaginably larger. The Milky Way wasn't the universe. It was just one galaxy among countless others, scattered through space like islands in an endless ocean. But Hubble wasn't done. His next discovery would be even more profound. He began measuring the light from these distant galaxies, analyzing their spectra, the rainbow of colors that their light breaks into when passed through a prism. And he noticed something strange. The spectral lines, distinctive patterns that correspond to specific elements, were shifted toward the red end of the spectrum. This red shift meant the galaxies were moving away from us. And not just moving away, but moving away faster the farther away they were. A galaxy twice as far away was receding twice as fast. This was Hubble's law. The farther away a galaxy is, the faster it's moving away from us. But what did this mean? It meant the universe was expanding. Think about dots on the surface of a balloon. If you inflate the balloon, every dot moves away from every other dot. The dots aren't moving through the surface itself is stretching, carrying them along. That's what's happening to space itself. Galaxies aren't moving through space. Space is expanding, and galaxies are being carried along with it. This was revolutionary. It meant the universe had a history. It meant it was changing, evolving, dynamic. It meant that, if you ran time backward, the universe must have been smaller in the past, denser, hotter. It meant the universe had a beginning. Now we arrive at perhaps the most profound question of all. Where did everything come from? If the universe is expanding, then wind the clock backward far enough, and everything, all the galaxies, all the stars, all the matter and energy in existence, must have been compressed into an infinitesimally small point. And then that point expanded. This is what we now call the Big Bang, though that name was actually given mockingly by a scientist who didn't believe the theory. He thought the idea was absurd. How could everything come from nothing? How could the universe have a beginning? But the evidence kept mounting. In the 1940s, a physicist named Georg Gamow and his colleagues worked out what should have happened in the first few minutes after the Big Bang. The universe would have been unimaginably hot and dense, a roiling sea of energy and elementary particles. As it expanded, it cooled. Within the first 3 minutes, protons and neutrons began combining to form the first atomic nuclei, mostly hydrogen, some helium, traces of lithium. This is Big Bang nucleosynthesis, and it explains why the universe is mostly hydrogen and helium even now, 13.8 billion years later. But here's the crucial prediction. After about 380,000 years, the universe would have cooled enough for electrons to combine with those nuclei and form the first atoms. When that happened, light would have suddenly been free to travel through space without constantly scattering off free electrons. That light, the light from when the universe first became transparent, should still be out there, stretched by the expansion of the universe from visible light into microwaves. It should be everywhere, coming from every direction, a faint whisper of the universe's birth. For years, this remained just a prediction. Then, in 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and William Wilson, were trying to eliminate a persistent hiss in their antenna. No matter what they did, no matter which direction they pointed their equipment, this annoying microwave noise was there. They checked everything. They even cleaned out pigeon droppings from the antenna, thinking that might be the source of the interference. But the hiss remained. Finally, they contacted physicists at nearby Princeton University who realized what they had found. This wasn't interference. This was it. This was the cosmic microwave background, the afterglow of the Big Bang itself. Suddenly, the Big Bang theory wasn't speculation anymore. It was observed fact. Since then, we've measured that cosmic microwave background with exquisite precision. We've mapped tiny variations in its temperature, fluctuations that represent the seeds of all future structure, the slight density differences that would eventually grow into galaxies and galaxy clusters. We've observed how galaxies are distributed and how they evolve over time, and it all fits the Big Bang model. But let's pause here and feel the weight of what this means. 13.8 billion years ago, give or take 100 million years, everything that exists, all the matter, all the energy, all the space itself, emerged from an incredibly hot, incredibly dense state. We don't know what caused it. We don't know what, if anything, came before it. Those questions might not even make sense because time itself began with the Big Bang. From that beginning, the universe expanded and cooled. Within the first fraction of a second, the fundamental forces separated from each other. Gravity, electromagnetism, the nuclear forces. Elementary particles formed. The universe was a seething plasma, too hot for atoms to exist. Then, after 380,000 years, the first atoms emerged. And then, darkness. The universe entered what we call the Dark Ages, a time with no stars yet, just clouds of hydrogen and helium slowly collapsing under their own gravity. And perhaps 100 million years after the Big Bang, the first stars ignited. Massive, brilliant, short-lived stars that fused hydrogen into helium and helium into heavier elements, carbon, oxygen, iron. When these first stars exploded as supernovae, they scattered those heavier elements into space, enriching the cosmos with the raw materials for planets and, eventually, life. Galaxies formed from the merger of smaller structures. Our own Milky Way cannibalized dozens of smaller galaxies over billions of years, growing through cosmic violence into the majestic spiral we see today. About 9 billion years after the Big Bang, in an unremarkable region of an unremarkable galaxy, a cloud of gas and dust began to collapse. Most of the material fell into the center, igniting to become a star, our sun, and the remaining material formed a disk that gradually coalesced into planets. One of those planets was just the right distance from its star, not too hot, not too cold. It had water. It had an atmosphere. And in that water, about 3.8. But our story of cosmology doesn't end with the Big Bang and the formation of galaxies and stars. In fact, in the past few decades, we've discovered that everything we've been talking about, all the stars, all the galaxies, all the matter we can see, makes up only about 5% of the universe. The rest? We call it dark matter and dark energy, and we barely understand them at all. Let me tell you how we discovered these cosmic mysteries. In the 1970s, an astronomer named Vera Rubin was studying how galaxies rotate. She was measuring the speed of stars at different distances from the center of galaxies, expecting to find something straightforward. Stars closer to the center should move faster than stars farther out, just like planets closer to the sun move faster than planets farther out. But that's not what she found. Stars at the edge of galaxies were moving just as fast as stars near the center. In fact, the rotational velocity stayed roughly constant no matter how far out you looked. This didn't make sense. According to Newton's laws, which still work perfectly well for this kind of problem, the only way this could happen is if there was much more mass in the galaxy than we could see. A lot more. The visible stars, the gas clouds, the dust, all the stuff we can observe with telescopes, this accounted for only a fraction of the gravitational pull needed to explain the rotation. There had to be something else, something we couldn't see, something that didn't emit light or absorb light or interact with light in any way we could detect, something dark. We call it dark matter, and we now know it makes up about 27% of the universe. It surrounds galaxies in vast halos. It clusters. It has gravity. But we don't know what it is. Is it exotic particles we haven't discovered yet? Is it something stranger? Scientists are building detectors deep underground, shielded from cosmic rays, hoping to catch dark matter particles interacting with ordinary matter. So far, we haven't found anything definitive. But dark matter isn't even the biggest mystery. In the 1990s, two teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic distance markers. They were trying to measure how the expansion of the universe was slowing down over time. Because it should be slowing down, right? Gravity is attractive. All the matter in the universe should be pulling on all the other matter, gradually slowing the expansion, maybe eventually reversing it. But the measurements showed something shocking. The expansion of the universe is not slowing down, it's speeding up. Imagine throwing a ball in the air, and instead of slowing down and falling back, it accelerates upward, moving faster and faster. That's what the universe is doing. Something is pushing space apart, working against gravity, driving the accelerated expansion. We call it dark energy, and it makes up about 68% of the universe. We have no idea what it is. Maybe it's the energy of empty space itself, the vacuum energy predicted by quantum mechanics. Maybe it's a new field permeating all of space. Maybe our understanding of gravity is incomplete, and on cosmic scales, gravity behaves differently than we think. We don't know. Let that sink in for a moment. We've come so far. We've figured out the age of the universe, traced its history back to the first fraction of a second, understood how stars and galaxies formed. We've peered into the structure of atoms and probed the far reaches of space. And yet, we don't know what 95% of the universe is made of. It's humbling. It's exciting. It means the universe still has secrets to tell us, mysteries to solve, wonders to discover. Before we continue deeper into modern mysteries, we need to talk about Einstein. We need to talk about how he completely reimagined what space and time actually are. Newton had given us a universe of absolute space and absolute time, a fixed stage on which the drama of matter and motion played out. Space was just emptiness, a container, and time ticked forward uniformly, the same for everyone, everywhere. But in 1905, a 26-year-old patent clerk in Switzerland published a paper that shattered these assumptions. Einstein had been thinking about light. Maxwell's equations, the laws of electromagnetism, predicted that light travels at a specific speed, about 300,000 kilometers per second. But Maxwell's equations didn't say, fast relative to what? They just said, this is the speed of light, period. This troubled Einstein. If you're standing still and you see a beam of light pass by at 300,000 kilometers per second, and then you start running in the same direction as the light beam, shouldn't you measure the light as moving slower relative to you? But Maxwell's equations seem to say no. The speed of light should be the same no matter how you're moving. Einstein realized that if the speed of light is truly constant for all observers, then something else has to give. And what has to give is our common sense notions about space and time. He worked out the mathematics, and he discovered something astounding. Time itself is relative. Two observers moving at different speeds will disagree about how much time has elapsed between two events. Moving clocks run slow. Length contracts. Simultaneity, the idea of now, isn't universal. This is special relativity, and it sounds crazy, but it's been verified in countless experiments. Atomic clocks on airplanes run at a slightly different rates than atomic clocks on the ground. Particles in accelerators live longer than they should because of time dilation. GPS satellites have to account for relativistic effects, or your phone's maps would be useless. But Einstein didn't stop there. He kept thinking. Special relativity worked for objects moving at constant speeds. But what about acceleration? And what about gravity? And then he had an insight, what he later called the happiest thought of his life. He realized that you can't tell the difference between acceleration and gravity. If you're in an elevator accelerating upward, you feel pressed to the floor, just as if gravity had gotten stronger. If you're in free fall, you feel weightless, just as if gravity had disappeared. What if gravity and acceleration are the same thing? What if gravity isn't a force at all, but the result of space and time being curved? He spent 10 years working out the mathematics, and in 1915 he published his theory of general relativity. In Einstein's view, space and time form a unified four-dimensional fabric, space-time, and massive objects curve this fabric. The sun creates a depression in space-time, and Earth rolls around that depression not because it's being pulled by a force, but because it's following the straightest possible path through curved space-time. A massive object warps space and time around it. Time runs slower in strong gravitational fields. Space is stretched and compressed. It sounds like science fiction, but we can measure these effects. Time runs faster on GPS satellites than on Earth's surface, and we have to correct for this. Light from distant stars bends as it passes near the sun, exactly as Einstein predicted. And in 2015, 100 years after Einstein published his theory, we detected something he predicted but thought we might never observe: gravitational waves. When massive objects accelerate, especially when they orbit each other, they create ripples in space-time itself, like ripples on a pond. These waves spread outward at the speed of light, stretching and compressing space as they pass. On September 14, 2015, two observatories in the United States, thousands of miles apart, detected a gravitational wave from two black holes that had spiraled into each other and merged 1.3 billion light-years away. The signal lasted less than 1 second, but it was exactly what Einstein's equations predicted. We heard the universe ring like a bell. We're listening to the symphony of space-time itself. Think about what this means. We've been observing the universe through light, electromagnetic waves, for all of human history. Now we have a completely new sense, a new way of perceiving the cosmos. We can detect events that don't emit light at all: black holes colliding in the darkness, neutron stars merging, maybe even ripples from the Big Bang itself. The universe is more than we see. It's weirder than we imagined, and we're just beginning to explore it. Now we need to zoom in, way in. We've been talking about the very large, galaxies, the universe, space-time, but cosmology also cares about the very small, Because to understand the first moments of the Big Bang, we need to understand quantum mechanics. Quantum mechanics is the physics of the very small, atoms, electrons, photons, the fundamental particles that make up everything. And it's deeply strange. Reality at the quantum level doesn't work the way reality works in our everyday experience. Let me give you a taste of this strangeness. An electron isn't a tiny ball. It's not a thing with a definite position and a definite velocity. Before you measure it, it's described by a wave function, a mathematical object that gives you probabilities for where it might be, how fast it might be moving. And it's not just that we don't know where it is, it doesn't have a definite position until we measure it. The act of measurement forces the electron to choose a position, to collapse from a cloud of probability into a specific location. Two particles can become entangled so that measuring one instantly affects the other, even if they're separated by vast distances. Einstein hated this. He called it spooky action at a distance. But it's real. We've tested it. The universe is non-local in a way that violates our intuitions about how separated things should behave. A particle can be in two places at once. Light is both a wave and a particle depending on how you observe it. You can't know both the position and momentum of a particle with perfect precision. There's a fundamental uncertainty built into reality itself. Why am I telling you this? Because in the first moments after the Big Bang, the universe was so small and so dense that quantum effects dominated. To understand the origin of the universe, we need to combine quantum mechanics and general relativity. But here's the problem. These two theories don't play nicely together. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and forces at tiny scales. Both theories are spectacularly successful in their domains, but when you try to apply quantum mechanics to gravity itself, the mathematics breaks down. You get infinities, nonsensical answers. For decades, physicists have been trying to find a theory of quantum gravity, a framework that would explain how gravity works at the quantum level, that would unite our understanding of the very large and the very small. String theory is one attempt. It proposes that fundamental particles aren't point-like, but tiny vibrating strings. Different vibration patterns correspond to different particles, and in string theory, gravity emerges naturally. But string theory requires extra dimensions, not just the 3 dimensions of space and 1 of time that we experience, but 10 or 11 dimensions total, with the extra ones curled up so small we don't notice them. Is string theory right? We don't know. It makes predictions that we can't yet test. Some physicists love it for its mathematical beauty, others criticize it as untestable speculation. Loop quantum gravity is another approach. It suggests that space-time itself is quantized, made of discrete units like pixels on a screen, rather than being smooth and continuous. And there are other ideas, other approaches, each with passionate advocates. The truth is, we don't have a complete theory of quantum gravity yet, and until we do, we can't fully understand the very beginning of the universe, the first 10 to the minus 43 seconds after the Big Bang, what we call the Planck epoch, when quantum effects and gravity were equally important. But here's what we can say. Quantum mechanics seems to be telling us that the universe is fundamentally probabilistic, not deterministic. Einstein's clockwork universe, where if you know everything about the present, you can predict everything about the future, that universe is gone. At the quantum level, God does play dice. And yet, from this quantum randomness, from this uncertainty and probability, emerges the structured, predictable universe we see around us. Somehow, the quantum and the classical coexist. Somehow, the fog of probability gives rise to the solid reality we experience. This is still mysterious, still unsolved, still wonderful. We've traveled far together, you and I, from ancient shepherds looking up at the night sky, to Einstein riding beams of light in his imagination, to modern cosmologists peering back to the edge of the observable universe. And now, as our journey nears an end, let's talk about the questions we still can't answer, the mysteries that keep cosmologists awake at night, the edges of our understanding where wonder and frustration mix together. What caused the Big Bang? We can trace the universe back to a fraction of a second after the Big Bang. We can describe in detail what happened as the universe expanded and cooled. But the moment of the Big Bang itself, why it happened, what caused it, whether caused even makes sense in this context, we don't know. Some physicists propose that our universe is just one bubble in an eternal, ever-inflating multiverse. Some suggest it emerged as a quantum fluctuation from nothing. Some think time itself began with the Big Bang, and so asking what came before is like asking what's north of the North Pole, a meaningless question. We don't know. Will the universe end? We know the universe is expanding and that this expansion is accelerating. If dark energy remains constant, the universe will continue expanding forever, growing colder and darker. In trillions of years, all the stars will burn out. Galaxies will drift apart beyond each other's horizons. Eventually, even black holes will evaporate through a process called Hawking radiation. The universe might end in a big freeze, a cold, dark, nearly empty expanse where nothing interesting happens anymore. Or maybe dark energy will grow stronger, accelerating the expansion faster and faster until it tears apart galaxies, then solar systems, then atoms themselves in a big rip. Or maybe dark energy will reverse, pulling everything back together in a big crunch, collapsing back to a singularity, perhaps to bounce and start a new cycle. We don't know. Are we alone? In a universe with hundreds of billions of galaxies, each with hundreds of billions of stars, many with planets, surely life must exist elsewhere. The numbers seem to demand it. And yet, we haven't found any evidence of extraterrestrial life, no radio signals, no signs of vast alien civilizations reshaping their galaxies. Just silence. This is the Fermi paradox. Where is everybody? Maybe life is rarer than we think. Maybe intelligence is rarer still. Maybe civilizations tend to destroy themselves. Maybe they're out there, but space is so vast that we'll never meet. Maybe they're here, but we don't recognize the signs. We don't know. What is consciousness? Here's a cosmological question that sounds like philosophy. What is the relationship between matter and mind? How does consciousness, subjective experience, the feeling of what it's like to be you, arise from atoms and molecules following physical laws? This matters for cosmology because we are the universe observing itself. We are arrangements of matter that have become aware, that ask questions, that do science. The universe isn't just out there, it's also in here, in our minds, in our thoughts about the universe. Some physicists and philosophers wonder whether consciousness plays a role in quantum mechanics, in the collapse of the wave function. Others think consciousness is entirely a product of complex information processing in brains, with no special role in the fundamental laws of physics. We don't know. Why these laws? Why does the universe follow the particular laws of physics it does? Why is the speed of light 299,792,458 meters per second and not some other value? Why does gravity have the strength it has? Why do particles have the masses they have? Some numbers in physics, what we call fundamental constants, seem arbitrary. We can measure them, but we can't derive them from deeper principles. We just accept them as givens. But here's something eerie. Many of these constants seem fine-tuned for life. If gravity were slightly stronger or weaker, stars couldn't form the way they do. If the strong nuclear force were slightly different, carbon atoms couldn't form. If the cosmological constant, dark energy, were much larger, galaxies couldn't form. Change almost any fundamental constant by more than a few %, and you get a universe that's hostile to life as we know it. Is this just luck? Are there countless other universes with different constants, and we happen to live in one that allows observers? Is there some deeper principle we haven't discovered that explains why the constants have the values they do? We don't know. And maybe, just maybe, we don't know is a beautiful answer. Not a final answer, but an invitation, an opening, a reminder that the universe still has more to teach us. Every answer in the history of cosmology has led to new questions. Every mystery solved has revealed deeper mysteries. And that's not frustrating. It's thrilling. It means there's always more to discover, always new frontiers, always another horizon beyond the one we've just reached.